Hello, I'm Bukola Joseph. So we are going to be solving a problem on statistical physics, and this question has to do with Fermi-Dirac statistics. Okay, and so we have done that of Bose-Einstein in the last video. So we are going to be doing for Fermi-Dirac statistics. Okay, so let's see how we are going to solve this problem. Let me read the question. The question is on the board. I'll read from the manuscript. Okay. Show the possible arrangement of two indistinguishable particles M and N among three energy states. Assume this particle obey Fermi-Dirac statistics. Hence, calculate the weight of configuration W of this system. So, when we did Bose-Einstein, you know that Bose-Einstein does not obey the Pauli's exclusion principle. Okay, I hope you still remember what the Pauli's exclusion principle is all about. I'll say it again. The Pauli's exclusion principle states that no two fermions, okay, with half integer spin, uh, such as the proton, the electron, the neutron, can occupy the same quantum state simultaneously. Okay, so the Bose-Einstein statistics does not obey the Pauli's exclusion principle. Okay, now if you check the last video, you see that for the weight of computation, we're able to get 6. Now for Fermi-Dirac, on the other hand, it does obey. It obeys the Pauli's exclusion principle. So let's solve this problem together. So if we are going to solve this problem, this is what we will do. Okay. Now, they say we should find the possible arrangement of two indistinguishable particles M and N among three energy states. So it means we have solution. It means the energy state Gj is equal to 3, and then the number of particle nj is equal to what? 2. Okay, now they say we should show the possible arrangement. So we have three energy states. That's 1, 2, 3, and the particle is mn. All right, now this obeys the Pauli's exclusion principle. So we have m n. Let me use capital letter m. Okay, dash, and then I hope you are seeing what I'm doing. Then we'll be having m dash n, and then we have dash m n. So you can see. Okay, so you can't have two of them on the same energy state. You can't have mn on the same energy state. Okay, because the Fermi-Dirac obeys the Pauli's exclusion principle. Okay, so now this is it. So mind you, since they are indistinguishable, okay, since they are indistinguishable, it means you must not use m and n. You can use n, 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 because they are indistinguishable. Okay, they are indistinguishable. Sorry, there's supposed to be n here. Okay, so we have this. So it means we have 1, 2, 3 ways. We have 3 ways. Okay, I hope you are seeing what I'm doing. Now we want to find the weight of configuration. So there is a formula that we are going to be using to find the weight of configuration. And what is the formula? This is the formula. We have the weight J is equal to Gj factorial all over Gj minus Ng, close the bracket, factorial Nj factorial. So remember that Gj is the energy level, number of energy level, and then Nj is the number of particles. So let's substitute. We have Gj is equal to 3 all over Gj minus Nj. That's 3 minus 2. So we have 3 minus 2 factorial. I hope my head is not obstructing. 3 factorial. Then Nj, we have 2 factorial. So this becomes 3 factorial is what? 3 times 2 times 1 all over 3 minus 2 will give us 1. So we have 1 factorial, which is equivalent to what? 1, right? Then times 2 factorial is what? 2 times 1. So if we multiply this, we have 3 times 2 times 1 give us 6. Then 2 times 1 times 1 will give us 2. 6 divided by 2 will give us 3. So this is what? The weight of configuration. So we have found the weight of configuration W of this system for Fermi-Dirac statistics to be what? 3. Okay, I hope you enjoyed this video. If you have not seen that of Bose-Einstein, you can look at or check out the previous video on that of on Bose-Einstein, and you will see that the number of ways that the particles can be arranged is 6 ways. I'm still Bukola Joseph, the physics enthusiast. Bye.